Have you ever watched a machine do something that just feels impossible? You know, like translating a sentence in the blink of an eye, or somehow finding your face in a photo from 10 years ago. It feels like magic. Well, today, we're going to pull back that curtain. We're going to look right inside the machine and figure out how it actually learns. And that's the thing, isn't it? From the outside, it is pure magic. But this quote really hits the nail on the head. Once you get inside, there are no spells, no secret sauce. It's just numbers. Billions of them being added and multiplied at speeds we can barely even imagine. So that's the big question we're going to tackle. Is this whole AI thing some kind of unknowable force? Or is it just a process, a logical system that, if we break it down, we can all start to get our heads around? Trust me, by the end of this, that infamous black box is going to look a whole lot clearer. All right, let's do it. Let's pry the lid off this thing and see what's really going on. It all starts with a design that's actually inspired by the very thing between your ears, our own brains. Okay, so at its core, a neural network is basically just this, a series of layers made of simple little calculators we call neurons. The first layer takes in all the raw stuff, every single pixel from a photo, for example. The very last layer spits out the final answer, like cat or dog. And all the real work, all the thinking, that happens in all those hidden layers sandwiched in the middle. So, what is each one of these millions of tiny neurons actually doing? Well, you might be surprised to find out that its job is actually incredibly simple, maybe even a little boring. Every single neuron in the network just follows the same simple 4-step routine over and over. It gets some numbers from the previous layer. It multiplies each one by a weight, which is just a knob that dials up or down how important that signal is. Then it adds a bias. Think of it like a little thumb on the scale, a personal preference. And finally, based on that result, it decides whether to fire off its own signal to the next layer. That's it. That simple calculation is the building block for everything. A great way to think about it is like this voting committee. One single neuron's vote doesn't mean a thing. It's too simple. But when you get thousands or even millions of these neurons all casting their tiny, simple votes across multiple layers, well, that crowd starts to get surprisingly intelligent. But how in the world does this committee get smart? Because it definitely doesn't start out that way. The real secret to AI, the absolute core of it, isn't the structure. It's the process of learning from every single mistake it makes. So here's how it all begins. The network takes a look at some data, it runs through all its layers, and it makes a guess. That's what we call a forward pass. Then a clever bit of math called a loss function compares that guess to the actual right answer and calculates a penalty score. You can think of this loss as the sting of being wrong. And without that sting, there's no reason to change. I love this analogy because it makes it all so clear. Imagine you're shooting free throws, and you miss. What does your brain do? It instantly traces the error back. My elbow was out a bit, or I didn't flick my wrist. That's exactly what a process called back propagation does for the network. And then what do you do next? You adjust your form just a little for the next shot. That tiny adjustment, that's what we call gradient descent. So this is it. This is the two-step dance that powers almost all of modern AI. First, backpropagation. It works backward from the mistake, rewinding the whole process to figure out which of the millions of little weights were most to blame for the screw-up. Then, gradient descent steps in and gives each of those weights a tiny, tiny nudge in the right direction so that next time the guess will be just a little bit less wrong. Okay, let's make this super concrete. Imagine a really simple network, and its only job is to decide if a house is expensive based on these 3 features. Now, when it's just starting out, all of its internal weights, all those little importance knobs, are set completely randomly. It has absolutely no idea what it's doing. So we show it this house, a house that we know for a fact is expensive, but because the network is just a baby with random settings, it makes a wild guess. And in this case, it guesses not expensive. It's wrong. Immediately, that loss function kicks in and basically screams, "Whoa, big mistake!" The error score, the loss, is high. This sends a shockwave through the entire network, a signal that says, okay, whatever we just did, that was really, really wrong. We need to fix it. And this is the cool part. Backpropagation acts like a detective. It traces the error back and figures out, you know what? The weight we had on neighborhood was way too low. That should have been more important. Size needs a boost too. And maybe that age feature shouldn't matter quite so much. Then, gradient descent makes those little nudges. Now just imagine doing this not once, but millions of times with thousands of different houses. Okay, so let's zoom out.
After millions and millions of these tiny little corrections, something pretty incredible starts to emerge. The network isn't just fixing one mistake at a time anymore. It's actually starting to build a genuine, flexible understanding of the world.
You see, this is why having lots of layers is so powerful. The very first layers, they learn to see super simple things, like basic lines, edges, and patches of color in a picture. The layers after that take those simple lines and learn to combine them into more complex shapes, like an eye or a nose or a car tire. And then the final layers take those shapes and assemble them into whole objects, like a human face or a complete car. It's building up knowledge, from simple to complex, all by itself. And this is a really critical point. The network isn't learning a list of rules like, if it has whiskers and pointy ears, then it's a cat. That's too rigid. Instead, what it's actually doing is learning to carve out a sort of region in a massive high-dimensional space. Everything that looks like a cat gets mapped to one valley in this space, while dogs get mapped to another. So when it sees a new picture, it's just checking to see which valley it lands in. But, and this is a really big but, this way of learning is not perfect. Because these networks are just brilliant pattern matchers, they don't have common sense. And that leads to some very strange and very important weaknesses. You know, there's a huge difference between really learning something and just memorizing the answers for the test. When a network generalizes, it truly learns the concept of catness, so it can spot a cat it's never seen before. But sometimes it overfits. It just memorizes the specific cats in its training photos. It's like that student who aces the practice test but completely bombs the final exam because they never actually understood the subject. And this is where things can get really weird. This is a famous example. Researchers took a picture that a network correctly identified as a panda. Then they added a thin layer of digital noise, totally invisible to you or me, and showed it to the network again. Suddenly, the network declared with 99% certainty that it was looking at a gibbon. This proves they don't see things the way we do at all. They see a world of numbers and patterns that we can't. So when you put it all together, the simple little neurons, the layers, and this relentless cycle of trial and error, you end up with something that feels a lot less like a cold alien calculator and a lot more like, well, us. Because think about it, this four-step loop, it's not just for machines. It's universal. It's how a baby learns to walk. They try to take a step, they fall, that's the error, they trace the mistake, adjust their balance, and try again. It's how an athlete perfects their golf swing. It's how we learn, well, anything. The only real difference is a neural network can run through this cycle billions of times before you finished your morning coffee. So in the end, no, it isn't magic. What it is the result of an incredibly fast, scaled up, and relentless process of learning from your mistakes. And when you think about it like that, that might be the most fascinating and, dare I say, the most human thing a machine could ever learn to do.